In our third lesson in our trigonometry unit, we're going to focus on finding the area of polygons using trigonometry. There are a couple special cases that we're going to explore. First of all, we're going to focus on triangles, where we know the lengths of two of the sides, but the triangle may not be a right triangle. We know two of the sides and the included angle between those sides. The other situation is dealing with regular polygons, where we know that all the sides have equal lengths, where all the interior angles are congruent, all the central angles are congruent, and all of the sides are congruent. And so we're going to deal with those two situations. The first is hopefully the most straightforward. And it's one of those things where when we work through the exercise, or when we work through the example, you're going to say, that's it? And that's my hope, that's my dream, is that you hear this and you see this example and you say to yourself, this looks very manageable. So the first thing is sort of this explanation of why this works. In this case, we need to know the length of B, side B, the length of C, side C, and the measure of angle A, the angle that's between sides B and C. When we are finding the area of a triangle, we need to multiply 1/2 times this base times this perpendicular distance from this vertex to that base. And that's the height. Well, in trigonometry, if I know the measure of this angle and I know the length of this hypotenuse in this right triangle, then that means I can compute the length of this segment or this segment. And so that is going to be our exploration in this moment. We're going to use right triangle geometry and this right triangle here to say, hey, if I know the measure of this angle here, then the sine of this angle is going to be found by taking the opposite leg, h, for the height of this triangle, divided by the hypotenuse, side C. And so the sine of angle A is equal to h over c, which means that when I multiply both sides by the side C, I find out that c times the sine of the measure of angle A is equal to the height of this triangle. Therefore, the area is found by taking 1/2 times the base times c times the sine of that angle A. All right? Area is 1/2 times the product of these two sides, B and C, times the sine of the angle that's included between those two sides. So that's your formula. Make sure you have that down. We know that information, the measure between the two sides and the lengths of the two sides. And so here are two examples. And actually, I'm going to do one and you're going to do the other. So in this case, we have two sides and the included angle. Our formula is the area of the triangle is 1/2 times B times C times the sine of the angle between those two sides. Now, in the past, we would say, well, one of the sides is B, and then we need to know the perpendicular distance from this side to that opposite vertex, or maybe we need to know if this is the base, then we need to know the perpendicular distance from here all the way over to there, and whatever our situation is, the example that we're dealing with. So in this case, we know two sides, we know the angle between, so it doesn't matter which one is B and which one is C, we're going to multiply them together. All right, area is 1/2 times 11 times 6 times the sine of 57 degrees. All right, so let's multiply those. In our calculator, we're going to take 1 divided by 2 times 11 times 6 times the sine of 57. Check your answer and see if it gives you the same answer as me. I get 27.676, so I'm going to round that and call that 27.7. The area is approximately equal to 27.7 square meters. Try to do this second example, and then I will check that in your notes. Your job is to take 1/2 times the product of the two sides times the sine of the angle between those two sides. Pause the video. All right. Next, we get to chat about finding the areas in regular polygons. Now, we already did this back in Unit 7, all right? So back before spring break, we encountered this, and we tried to make sure that we could find the areas of these regular polygons. And we used special right triangles, specifically with equilateral triangles, squares, and regular hexagon. But today, we're going to focus on using trigonometry, using the measures of those central angles that are then cut in half when we draw that apothem to make sure that we can find the area of these polygons. So just a reminder, the area in a regular polygon is found by taking 1/2 times the apothem times the perimeter. We were only able to deal with these situations because the measure of this central angle we found was 360 divided by n. All right, remember the measure of the central angle is 360 over n. And in this case, 360 over 6 gives us 60 degrees. All right, so this angle right here is a 60-degree angle. This one is also a 60-degree angle. But when we would draw that apothem, it would cut that angle in half. And we would end up with a 30, 60, 90 triangle. All right, and then we could apply 30, 60, 90 rules. We are not going to apply 30, 60, 90 rules here today. Instead, we're going to use trigonometry to get that answer. So what I mean by that is we are going to try to figure out what this value is right here. All right? If I know this, then I know the length of the side because I just double it. This is 2x's is the side. And if I know one side, then I can multiply by 6 to get the total perimeter of that polygon. All right? So I have the apothem. I need to find the p-value, all right, the perimeter. And the perimeter is going to be 6 times the length of a side, and a side is 2x's. So let's use some trigonometry to solve for x. I can use 30 degrees or 60 degrees, but I'm going to go ahead and use 30. And we're going to write a decimal approximation for the value of x. I'll say that in this case, the tangent of 30 degrees is equal to x over 7. So 7 times the tangent of 30 is equal to x. That is going to be the length of this piece, which means that the whole side length is twice as big. A side is going to equal 2 times x. So in that case, 2 times 7 times the tangent of 30 is equal to one side of the polygon. So 14 times the tangent of 30 is equal to one side. But that is not the perimeter either. All of the sides are congruent, so we're going to take the number of sides to get the perimeter. 6 times 14 times the tangent of 30 is going to equal that perimeter. And so 6 times 14 is 60 and 24, which is 84. So the perimeter is 84 times the tangent of 30. Now we don't have to write all of that out. We can if we would like to, but the area is equal to 1/2 times the apothem times the perimeter, which in this case is 1/2 times 7, times the perimeter, 6 times 14 times the tangent of 30. What I'm doing is I'm not typing this in my calculator at the beginning. Because what I'm going to do is I would get an approximated value to one decimal place, and then I would take that error from that rounding and I would double it. And then I would multiply it by 6. And so I would exacerbate that error and make it even more generalized and more incorrect, more off. All right, so we want to be as accurate as possible. So we're not going to type anything in the calculator until the very end. So if this 14, that 2 times 7 bugs you, you can do 6 times 2 times 7. Or you can do 6 times 14. Or you can actually multiply 6 times 14 and get your 84 times the tangent of 30. But I think it's valuable to just kind of write this as is. And now we can just type this whole thing into our calculator as needed. 1/2 times 7 times 6 times 14 times the tangent of 30 degrees is going to give us our area. 169.7409, so I'm going to call it 169.7 square feet. This is the approximated area of this regular hexagon. All right, and that was not using special right triangles. So if you can't remember your special right triangles, but you're pretty good at trig, then you get to use trig and do some awesomeness. Again, if you are better at special right triangles, then maybe you'd like to use special right triangles here. The only issue is that when we're dealing with a situation like our pentagons, this is not a special right triangle, all right? The central angle, the 360 over n, is going to be 360 over 5, which means that the measure of one of these central angles is going to be 72 degrees, all right? So when I cut that in half, all right, I get to get 36 degrees, all right? If I take that apothem and I cut that 72-degree angle in half, I'm going to be down to 36 degrees. All right? And that's okay, but it's not going to solve our problems of not being able to use trig, right? We're going to have to use trig here. We can't use special right triangles because 36 degrees is not the measure of one of our special right triangles. We're still using the same formula, but what's going to happen is we have to kind of look at this little wedge right here in the middle, all right? We kind of cut this piece, and we've got the this apothem, this 36-degree angle, this 90-degree angle. I don't care that this one is 54 degrees. That's not helpful to me right now necessarily. I'm just not going to use it. We're going to focus on this little triangle and try to find the length of the apothem. Now, one thing that you'll notice is that I wrote a 4 here. Where did that 4 come from? Well, if the whole side is 8, then the apothem cuts that side into half, just like we did back in lesson 7.5. All right, so go back and watch that video if you need to review your central angle measures, or if you need to review how to find the apothem and how those side lengths are related, etc., etc. So in this case, we need to figure out what the apothem is using this 36-degree angle. And so from this perspective, we're using tangent again. That's going to be our magical recipe. The tangent of 36 degrees is equal to opposite over adjacent, or 4 over a. Which means through a couple steps, or if you can do this in one step, power to you, a times the tangent of 36 equals 4, or a is equal to 4 divided by the tangent of 36. Now, I don't want you to type that in the calculator. Instead, I want you to use this as your apothem in this exercise. So the area is 1/2 times the apothem, 4 over the tangent of 36, times the perimeter. We're not given the perimeter. We know the number of sides, and we know the length of each side, 5 times 8. So we can write that the perimeter is 40, or we can just leave it as 5 times 8, because we're going to use our calculator anyway. Now, the issue that you need to be aware of is, do you know how to utilize your calculator properly to do this multiplication? All right? The key here is you need to close your parentheses after your 36. All right? So let's type all of that into our calculator so we can see what that looks like. We're going to do 1 divided by 2, and then we are going to multiply that times 4 divided by the tangent of 36, close parentheses, and then we're going to multiply by 5 and by 8. When I do that, it's going to give me the area. 110.11 means I'm going to call that 110. The area is approximately 110.1 square centimeters. We're using trig to do some of that heavy lifting, and we don't have to worry about special right triangles or any of that other garbage. We get to go ahead and just use the central angles, understand that the radii bisect these angles, the apothem bisects the central angles, the apothem also bisects the opposite side there, or the side length cuts it from 8 to 4 and 4, and we get to work from there. All right, I have one more example that is in the PowerPoint, and that is working with an octagon, a regular octagon. And what's beautiful about this exercise is that I have all of the steps typed digitally, so you don't have to worry about my handwriting. But let's see if you can do this exercise. Pause the video. Let's see if you can calculate the area of this figure. Now, this is the worst case scenario. In the first example, we had the apothem, and we used that to find the side length. Once we had the side length, we could use 1/2 times apothem times perimeter. In the second example, we had the side length. We had to work that back so that we could know the apothem, and then we could do 1/2 times apothem times the number of sides times the length of each side. On this situation, we have the radius. Right? This is, again, just like last unit, just like the area unit, unit 7. The radius is like the worst piece of information, because that means you have to find both the side length and the apothem. So it's just kind of a double whammy. So this is an octagon. All right? Go ahead and let's see if you can find the apothem, find the value for x, double it to get the side, multiply by 8 to get the perimeter, multiply all that together, and multiply it by 1/2 to see if you can get the area. Pause the video if you need to do that. So working through this, you're going to find that the measure of the central angle, again, this is something that I do expect that you know. The measure of one of these central angles is found by taking 360 over n, all right? And so we find out that the measure of that central angle is 45. The issue with that angle being 45 degrees is that this is not a right triangle. So the 45 might be a little deceptive. You're not using 45, 45, 90 rules. All right, instead, when you draw in that apothem, it cuts that 45 degrees in half. And so now you're working with 22.5 degrees in this triangle. All right, you've got x, you need two x's to get a whole side. You've got the apothem. You are going to use trigonometry to find the apothem. You know the radius is 16, and you know the measure of this angle is 22.5 degrees. Okay, so the way that you are going to approach this is you're going to use sine to find x. You're going to use cosine to find a. All right? Now, the issue with this is that you want to leave these expressions for the value of a and the expression for the value of x in that multiplied form, not a decimal approximation. We never round until the end. We're going to use these exact values for x and the exact value for a in our multiplication. So watch what happens here when we think through this. All right? The area is found by taking 1/2 times apothem times perimeter. Now, we do not know what the a value is. All right? We do not know the x value, but I do know that the perimeter is going to equal 8 times 2 times x. If you need to pause and think about why that is, please pause and think about why that is. If you don't get why p is 8 times 2 times x, send me an email or write it in your notes and we'll talk about it. But here is 1/2 times the a value times the perimeter, 8 times 2 times x. We're going to try to find out what a is and what x is, all right? And we're going to try to find exact values, not decimal approximations. The way that we find the a value and the x value is by using the cosine of 22.5 is going to be adjacent over hypotenuse, a over 16. The sine of 22.5 is going to be opposite over hypotenuse, or x over 16. Which means that the a value is 16 times the cosine of 22.5, and the x value, or half of a side length, is 16 times the sine of 22.5. So if I know what a is, and I know what x is, then I can plug this in here. And if I know what x is, I can plug x in there, and then I can multiply using my calculator, closing and opening parentheses as needed. Pause if you need to think about why these are what they are, or be prepared to ask a question in class. When I plug those values in, I'm keeping the color coding here, hopefully it's helpful. You're legit just going to type that whole thing in your calculator. You're going to have open and close parentheses here, open and close parentheses there. You don't actually need these parentheses that I've got typed. All right? But when you type that all in, you get an approximated value of 724.1 square units. Right? I don't have square units given here, but that is the step-by-step process for finding the area given the radius of a regular polygon. All right, so we've done all three situations. We found the area given a side length, given the apothem, and given the radius, all using trigonometry.